This is Himabindu, Assistant Professor in IARE College. So today in this video, I would like to explain about the concepts of definitions and terminologies on pushdown automata. So what is meant by pushdown automata and how we are going to construct this pushdown automata? What are the important things for the construction of pushdown automata? We will see in this video. So what is the pushdown automata? PDA, pushdown automata. So what is the pushdown automata? Why we are going for the pushdown automata? So here pushdown automata is the tool to implement the CFL, context free languages. So here with the context free languages we can construct the pushdown automata. For the construction of pushdown automata we require the context free languages. The finite automata has, if you observe the Chomsky hierarchy, we have the regular grammars, or we have the automata. We will see the finite automata is the first, and second one is the pushdown automata, and third one is context linearly bound automata, and fourth one is Turing machines. So these are the models we got with what we have in the theory of computation. So in this one we are going to discuss about the pushdown automata. So pushdown automata, we require the languages called context free languages for the construction of pushdown automata. And what about this finite automata? So finite automata is a subset of, so finite automata is a subset of PDA, pushdown automata. That means we can also construct the pushdown automata for the finite automata. So whatever the languages of regular languages or grammars are there, we can also construct the pushdown automata for that languages. So here the pushdown automata. Why we go for the pushdown automata? We already have the finite automata. Why we need to go for the pushdown automata? In finite automata, we don't have so finite automata has no memory to remember the count of input symbols. Suppose here in finite automata, we can't construct the finite automata for a power n and b power n. So why? Because the counting memory of number of a's and b's are not there in the finite automata. So to remember those the values, we have to move to the PDA, pushdown automata. So that is why we are going to develop the pushdown automata. So finite automata, it is having the memory, it is not having the memory to remember the count of the input symbols or to match the relationship between the different types of symbols. So this kind of examples we can't construct the finite automata. So this can be constructed with the pushdown automata. So for this one, so in the finite automata, it cannot remember number of A's, how many number of A's are there and how many number of B's are there. So it can remember finite automata, we can construct A star, B star, but we cannot construct A power n and B power n. And this will be constructed by the pushdown automata. So that is why we are going to pushdown automata and define a pushdown automata. So a pushdown automata way to implement the context free grammars in a similar way to design the DFA. So while designing the DFA, we are going to start with the initial state and finite amount of memory, but in the PDA, can't remember the infinite amount of information. Basically, a pushdown automata is a finite state mission per stack. So this stack will count the number of elements in the input symbol. So for this one, we are going for the stack. So generally we have the how to define the finite automata, but with the additional memory we are going for the pushdown automata. A pushdown automata has three components. One is the input tape, and one is the control unit and the stack with the initial size. So these are the three things we are having in the pushdown automata. And how to represent the initial store of PDA. So PDA is nothing but we are saying that finite automata FSM plus stack. So this stack has the initial values. So that is represented as a initial store. Generally we will represent with the Z0. So initial store of the stack is generally represented with the Z0. And how to represent the PDA, pushdown automata. So finite automata, we are having the definition with the 5-tuple notation. Like that here also, we are just adding the stack to it. So FSM plus stack. So FSM, it is having the Q. So L is equal to, or M, pushdown automata, M is equal to. So Q is nothing but a finite amount of memory, a finite amount of states, and tau is nothing but the symbols, tau symbols. So what are the values we are going to insert into the stack? Those are all represented as a tau symbols. And P is the sigma. So sigma, which is having the alphabets like zeros and ones based on the input what we are taking. And delta is the transition function we'll discuss. And Q naught is the initial state, and Z naught is the initially stack symbol. So initialize the initial store, we can say that it is a initial store, that is nothing but a Z naught. Stack symbol initialization, and F is the final states. Based on the transition functions, how many final states are there? Those are all represented with the capital F. So this is the definition of pushdown automata. It is having, additionally we have the tau and the Z naught. So 7 tuple symbols are there. So in this one, tau and Z naught is the new values which was for the finite state mission. And how to represent the transition function. So generally for the FSM, we will write the transition. It is a current state. Q naught is the current state with the input symbol will lead to the next state. So next, this is the current state and this is the next state. And here input value. So this is for the FSM. And here we have the stack, and to include the values of stack symbols, we are having the 3 values. So what are those 3 values? So here Q is the number of states and P is the values input symbol. So sigma, so Q and sigma, and tau is nothing but what is the top of the stack symbol is there. So those are all the 3. So we need to represent here in the tau symbols, which leads to next state, that is a Q and tau symbol. And what we are going to replace for this input symbol. So what we are going to replace with for this input symbol. So this is the transition function for the pushdown automata. And what are the 7 tuples? We already discussed. The Q is a finite set, finite set of states, and tau is the stack symbols, and P is the input alphabet, and delta is the transition function. So here delta is equal to transition of Q comma sigma, and with the top of the stack symbol, which leads to the next state Q comma, and replacement of this input value, that is tau symbol. So Q comma tau symbol, and Q naught is the initial state and Z naught is the initially what is the top of the stack symbol is there. We will represent with the Z naught, and F is the accepting states or final states. So these are the 7 tuple. So 7 tuples for the pushdown automata. And how many operations are performed? So we are using the stack symbol. So what are the operations we are going to perform on the stack? So we can push and pop operations are going to be there in the stack. So one is a push and one is a pop. So in the push operation, a new symbol is going to be added on the top of the stack. And pop symbol is while reading one input, we will pop the values from the stack. So these are the 2 operations which we are going to perform on the stack. And what is how to represent the empty stack initially? So empty stack will represent generally with the, so generally we have to represent with the Z naught initialize, and when we appear on the Z naught, we need to remove that. That is nothing but pop. We need to pop the Z naught so that the stack is fully empty. So initially the empty stack initially. So that is nothing but a dollar. To represent that, instead of Z naught, we will represent with the dollar like this. And define deterministic context-free languages. So here in the context-free languages types, so we have two types. One is deterministic context-free languages and non-deterministic context-free languages. So here we have two types and a subset of CFL. So it is a deterministic CFL, or it is a subset of CFL. It is a subset of CFL and recognized by the Pushdown Automata. And deterministic PDA has only one move from one given state. So generally for the determinism, we have to from one state we have the value with the 0 to 1 state only. It is moving to the next state. And this is a DFA and DFA or determinism. And here coming to the non-deterministic, so it is moving to the two states with the 0 input. So this is NFA. So here determinism is nothing but the given state and input symbol. One move from the given state and input symbol. So, and that's why it is a subset of CFL, context-free languages. Show the notation of empty string in the PDA. So, how we will generally represent empty string in the sense. So, after reading this input symbol, we have, whenever we reach the Z naught, so to represent the transition, so it is empty. So, transition of Q naught comma epsilon with the top of the stack symbol Z naught should be named the Q2. So that is nothing but after reading, emptying the string, after reading all the string, we will name the empty string as a epsilon here or by lambda also. Show the notation of input state in the PDA. So input state or initial state, how generally we will represent with the Q naught only. And what is mean by empty stack acceptability? So we have the two types of acceptabilities in the Pushdown Automata. One is the empty stack acceptability and final state acceptability. Generally, after this, after reading all the string, when we reach the end of the stack, so that is initializing the stack symbol. So when we reach this, so after reading we just popped and replaced the values with the x, and we reached the value Z naught. So after reading this string, we have the empty string and we have the value Z naught. So Z naught, while reaching the Z naught, when we talk about the empty stack, we need to empty the stack also. That is nothing but we need to pop that. So popping that value, that is Q naught, Z naught, empty the string, and so Z naught is there, top of the stack symbol is Z naught. We need to pop with and move to the next state. So that is nothing but popping means we know we are not having any value here in the stack. Even also even the initialized stack symbol also not there. So when we appear Z naught in the stack, we need to pop that value also, so that the stack is fully empty. So that after reaching the after reading all the input string, when we reach the empty stack, we can say that it is a empty stack acceptability. So these are the rules. So language W, so Q naught and W is the word what we are taking as an input, and I is the initializing the stack symbol, and which is a term. Fallen T is nothing but all the moves, instantaneous descriptions, and star moving to the emptying the string. So finally we don't have any value in the string. So that represents the empty string, and which Q belongs to capital Q. So this is about the empty stack acceptability. And show the notation of output states, that is nothing but a final state or acceptance state. Generally we'll represent the value with the double circle. So here also the final state is going to be represented with the double circle. That is nothing but output state is generally represented with the double circle. And define acceptance of PDA by final state. So we told that we have two types of PDAs. One is the empty stack acceptability and second one is the final state acceptability. So in the empty stack acceptability, the stack is fully empty. So after reaching Z0, this Z0 is going to be replaced and this stack is fully empty. So this is the empty stack. And coming to the final state. So when we reach, after reading the value, so here A, B I am taking. So after reading the value, we got the value of epsilon. After reading the value, and finally we have the general Z0 is there. So after reading the value of 4 values, when we got the input string as a epsilon, so Q0 is the initial state, and so top of the stack symbol is Z0, and what is the input string is epsilon. Input string is epsilon, and top of the stack symbol is Z2. And what we need to do? So we need to simply do the same thing, and we need to replace the value with the same Z0 only. That is Q2. We are moving to the final state, and we need to replace the epsilon with Z0 only. So that nothing but Z0 we are not going to be changed. So the top of the stack symbol is not going to be changed. So when we reach this final state, we can say that, so when we reach the Z0, our initial top of the stack symbol Z0, we can say that it is a final state acceptability. Final state acceptability. So generally the language which we have here, so whatever there top of the stack symbol is there, so X is there, and we have the final state, that is nothing but it is reaching the final state. This Q is nothing but the Q belongs to the final state, and this epsilon is nothing but, so while reading the epsilon, whatever there in the top of the stack symbol, that is going to be replaced with the same symbol, and what we can say that it is reached the final state. So that it is the final state acceptability happened for the pushdown automata. And define acceptance of PDA by empty stack. So empty stack acceptability. So here we have the two pushdown automata and emptying the stack. So after moving the Z0, we are going to replace with the Z0, and we are going to emptying. We are pop the Z0, and we need to write the empty string. That is nothing but empty stack acceptability. And what is the different symbol between two states in a PDA? So PDA, two states are there here, initial state and a final state. Generally we'll represent with the two states in between, we'll represent with the arrow mark. So here this is the notation of the transition symbol between two states in a PDA. Why input tape is used in PDA? So why we are going to use this input tape in the PDA? So in first we discussed about the number of amount of memory what we are having for the count for the number of elements in the string. To count the values, we require the memory. So we require the infinite or input tape we require. So that's why we need to go for the input tape. So that input tape is buffer which is divided into cells, and each cell stores a symbol, input symbol from the given string input symbols, and read by control head, and from left to right we can move in the string. So these are the inputs in tape. So this is tape which is having the values like this, and the header can move from after reading this string, it is moving to the next head. Like this, the header controller is there in this input tape. So why stack is used in a PDA? So why we go for the stack? So earlier we discussed. So stack, the finite control reads the input symbol and place them in the stack. And what is the operation, data structure operation? First in, last in, first out. So last in, first out. So here while reading the string, so whenever A is there, we need to substitute capital A is there, we need to substitute A. Then so here, how to read this after this one, how to read this string. So here A is there, the string. So while reading A, so which A we need to take? So this is the first A. So last what we inserted, we need to take this input string, and whether the operations like push or pop operation going to be performed on the last in, first out. So last what we inserted, we need to do the first operation for the last one. So this is the last in, first one, last in, first out we are going to use in the pushdown automata stack. And why pop operations is used in the pushdown automata? So why we have while reading the input symbols from input tape, based on the condition, the top of the stack symbol is popped from the stack to recognize a particular string. So to recognize, so whether the string given is having the pattern or not, we need to check. So to check that one, first we need to insert, and then we'll pop. The popping and pushing operations matched, we can say that the stack is, so the stack, so the input string what we got is the constructed PDA is correct or not, we can check with the stack only. So that is the why we are going to use the operations, push and pop operations for the stack. Why push operation is used in PDA? So while reading the symbols, so why push operations? From the input symbol, finite control will push into the top of the stack symbol. So push operation, why we go for the push operation? To read the value, to check the pattern of the string, first we need to push the values into the stack. Then the count of the number of A's or B's there. So according to the how many A's are there, we need to check the number of A's and we can pop accordingly. So that is why we are going to use the push and pop operations in the stack. And what is the non-deterministic PDA? So we have two types of PDA. One is the non-deterministic and deterministic pushdown automata. So coming to the non-deterministic pushdown automata, non-pushdown automata, non-deterministic. Conceptually, non-deterministic pushdown automata is similar to NFA. So non-deterministic finite automata, it is similar to non-deterministic finite automata. In PDA, there should be multiple transitions for unique input. So for a single input, we are having multiple states. The construction of pushdown on is much more simplest than pushdown automata. So here the simplification or construction of a non-deterministic pushdown automata is also simplest than a pushdown automata. And condition for the converting CFG to pushdown automata. What are the conditions? So whenever the grammar is given, we need to convert into a pushdown automata. That is nothing but we'll take the example. So input is S tends to A, capital A, and S tends to A is there. So we need to convert it to a transition diagram first. Then we can convert the pushdown automata. And here, so transition function, so S tends to A is there, and we can write and A like this. So for the same state, we can write, so we can write the transition. So we can convert the grammar into a pushdown automata. So rules first and or H's in the terminal symbols when we want to convert CFG into a PD, push-down automata. And why two stacks are used in push-down automata? So while some languages, all the languages will not require a single stack. So some languages, so the certain languages which cannot be accepted by the single, which cannot be accepted by the push-down automata with a single stack, then we have to use the two checks or to perform the special case when we want to perform the two checks on the input string. We will use the two stacks in a PDA. So to when we perform, so here in one stack we will check one time for the number of A's and B's, like that. So in certain languages we need to double check the string. So that kind of languages will require the two stacks for the construction of push-down automata. And why finite automata is less powerful than push-down automata? So finite automata is it is a subset of push-down automata. So we cannot construct all the finite automata cannot construct all the languages constructed for the all the languages of regular languages. But it is we can construct push-down automata can be constructed for even regular languages also. That's why the PDA is more powerful than finite automata. And what is the instantaneous description? So while doing the transitions in a pushdown automata, we require the instantaneous description. So what this instantaneous description is nothing but it is a triple notation. So one is the state and W is the string and Y is the top of the stack symbol. So here, and which is a Q is a state and W is the remaining input string and Y is the stack content. So these are the three tuple notation for the instantaneous description. So this instantaneous description generally will represent with the fallen T, and this fallen T is a multiple moves. So it is a one move. If you represent a one T, so it is a one move from one state to next state. Like that, how many states are there for the entire PDA? So those are all represented as a turnstile notation star. So this is nothing but an instantaneous description. And show the PDA mission configuration. So here the mission configuration of the element K cross sigma. So that K and tau star. So K is the value constant, so stack constant and current state. So what are the values of elements, capital letters or states, number of states are required with the capital K. And sigma is nothing but what are the input symbols. So how many input symbols are there, and tau star is nothing but what are the stack symbols are there, how many times it is having in the stack. Those are all represented as a three things, that is nothing but a tuple notation, that is instantaneous description. And show the conditions to accept the string in PDA. So what are the conditions we need to string which is having in the PDA? So the W is the accepted by the pushdown automata if and only the turnstile star. So this is all the moves which are represented in the one single notation. So if S, W, E. So what is this S? So S is the start symbol. S is the start symbol. And W is the unconsumed input. Unconsumed. So input, and E is the, so E is nothing but the initial stack symbol. So stack symbol, initial stack symbols. So after reaching all the values, we have to get for the final state, that is a capital small e. That is nothing but we need to empty that stack. Initialize the stack and then empty that stack. So this is about the conditions to accept the string in PDU. And what is the difference or different types of languages accepted by the pushdown automata? One is the initial state, final state acceptability, and empty stack acceptability. We already discussed. And what is the significance of pushdown automata? Why we go for the pushdown automata? The finite automata used to model the regular expression and cannot be used to represent the non-regular languages. So finite automata generally will construct for the regular languages and regular grammars, but we cannot construct the finite automata for non-regular languages. So suppose like a power n, b power n kind of thing. So in this example, we need to count the number of a's. Why? Because the number of a's, how many a's are there, number of b should be compulsory, b's should be followed. To count how many a's are there, there is no requirement, there is no possibility in the finite automata. So to count the number of a's or b's elements in the input symbol, we need an additional memory. That is nothing but additionally we require the memory. So here the additional memory is having in the pushdown automata. That is nothing but the stack is added here. So that's why we cannot construct the finite automata for non-regular languages. So here we can construct the pushdown automata for the non-regular languages. And when is the string accepted by the pushdown automata? So here the input string is accepted by the pushdown automata if the final state is reached or emptying the stack. So this already we discussed. So final state. So how to find the final state? It is final state reach. So whenever we appear Z0, so after completing all the input string, whenever we are reaching the string, for the empty string, we are reaching the Z0 symbol. So we can say that it is the final state. And we have one more type, empty stack. So after reading all the input string, we got empty the string. So we can say that it is the empty stack acceptability. So these are all about the pushdown automata and what are the definitions we have. So here in this one, for important one, empty stack, final state acceptability. So final state acceptability. And second one, empty stack acceptability, empty stack. And so general representation of stack. So stack operations. And fourth one, so here general instantaneous descriptions, and how to represent deterministic, non-deterministic. So NPDA, and so these are all the things what we have to observe in the pushdown automata. So this is about the definitions, all definitions in the pushdown automata unit. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.